This is the second video of hypothesis testing about a population mean. Let's get right to the problem, and we're going to work through the remainder of the problems in this unit pretty quickly. According to the World Almanac and Book of Facts 1999, the average velocity of a typical garden snail is 13 millimeters per second. A new species of garden snail was discovered, and a study was conducted to see if this new species could keep up with the more well-known species. The study consisted of 9 snails, and their mean velocity ended up being 12.62 millimeters per second, with a standard deviation of 0.49 millimeters per second. With a 0.01 level of significance, test to see if this study showed that the new species of garden snail is likely slower than the more well-known garden snail. Here's a list of things that we are going to eventually have to do. Same as on the last problem. Determine whether this is a test of mean or proportion. It's a test of mean. We're talking about averages. Determine the correct sampling distribution that should be used. So the question is sigma known or not? And it said the study consisted of 9 snails, and their mean velocity ended up being 12.62 millimeters per second, and the standard deviation was 0.5 millimeters per second. Although this is showing a standard deviation, it is not showing the population standard deviation. If it doesn't specifically use the word population, or if it doesn't say sigma equals, then basically sigma is unknown, and this is an S, not a sigma. Let's deconstruct the problem. First, we would need to know what X bar is. That's the sample mean for the problem. And the sample mean, in other words, the mean that comes from the study, is 12.62 millimeters per second. The total number of people or things in the sample, it says right here, there were 9 snails. So that would be our answer right there. Okay, the Greek letter nu, we went over this in the last problem. Nu is a very simple calculation. It means the degrees of freedom in such problems, and the calculation is simply n minus 1. So for this problem, nu is 9 minus 1, which equals 8. And it's only necessary if sigma is unknown for the problem. But we already determined that sigma is not known. Therefore, this value nu will be necessary. Mu, the value we're testing against, or the value for the mean prior to this study, or what is known as truth. Before this thing was tested, the garden snail moved at 13 millimeters per second. That would be what our truth is. Next, we want to know the level of confidence. We always express levels of confidence as a decimal when we put them in on the spreadsheet, although typically they're shown in a problem as a percent. In this problem, we are given a level of significance as 0.01, so my level of confidence would be 0.99. Alpha is 1 minus my level of confidence, and this is also called the level of significance, and that was given to us in the problem as 0.01. Lowercase sigma, it's the population standard deviation. This is not given to us in the problem, so we have to use S instead, or some other measure, but S is given to us, so that's the one we use, and it's given to us as 0.49. Here I have the setup of everything that I would have to just plug directly into the spreadsheet. Next, we have determine whether this test of mean or proportion. Already done that. It's a test of mean. And determine the correct sampling distribution. Because this is a test of mean, but sigma is not known, we use this thing we call the t-distribution. We already used the t-distribution for confidence intervals, but I'll show it to you again. Determine if this test is a left tail, two tail, or right tail test. The keywords slower than indicates that this is probably a left tail test. And again, not necessarily so. These problems can be tricky from time to time. We set up our null and alternate hypotheses. We have mu equals 13 because that's the value that we're testing against. The garden snail, 13 millimeters per second. And because it's a left tail test, we set up our alternate hypothesis as mu is less than 13. Determine the critical values in rejection regions, etc., etc. For a left-tail test of mean with sigma not known, we use the Excel function t.inv of alpha comma nu, or t.inv alpha comma degrees of freedom. Let's put in the numbers that we have. We have an x bar of 12.62. We have n of 9. So this automatically calculates nu. We have a level of confidence of 0.99, I believe, for this problem. And yep, that's what it is, 0.99. Alpha is automatically computed as 0.01, and that matches with what we're given in the problem. And alpha over 2 is also calculated as simply dividing alpha by 2. Mu for this problem, again, the value we're testing against is 13. And sigma for this problem is 0.49. We need to know which of these two boxes. And remember, I have it labeled. It says if sigma is known, we use this one. But sigma is not known, so we go to this one. S is simply just a direct reference to another cell. I'm just going to type in equals, and I'm going to click on the cell where I have sigma or S equals. And you'll see whatever number you put in this box will also show up in this cell right here. So for a left tail critical value, and this happens to be a left tail test, but we'll go through all of these. We're going to say equals t dot inv, open parenthesis, alpha, which is this value right here, comma, nu, or my degrees of freedom, which is right here, and close parenthesis, and that gives me a negative value, the negative 2.89645, etc. In order to get the right tail critical value, we do what we had done in the green box above, and we just take the absolute value of whatever the left tail critical value is. So I'll type in equals absolute value, which is ABS. Click on that cell, close parenthesis, press enter. A two-tail critical value for a t distribution. We don't actually need alpha over 2 for that. We have a special function that they have for the t distribution that we don't have for the standard normal distribution or the norm.s.inv function. And that is t.inv.2t. And what that is, it will split up your alpha value directly into two tails. So in other words, for this one, I'm going to type in equals t.inv. And if you see all the way down here, it's .2t. And again, it's just simply alpha comma nu, and alpha is right here. Remember, we're not going to use alpha over 2 when we're using the t distribution. We're going to use the better function that we have that automatically divides alpha into two tails, comma nu, close parenthesis, and press enter, and it gives me my two-tail critical value. We've already determined that it is a left tail test because the word slower than. That would mean that my critical value on the left tail is negative 2.89645. Let's see what information we have and what we still need. We have x bar, n, nu, mu, level of confidence, alpha, alpha over 2, sigma, well, it's not needed if we have S. This is going to be a test about a population mean with sigma not known. So the sampling distribution is the t-distribution. The keyword slower than indicates it's a left-tail test, which means that my null hypothesis is mu equals 13. My alternate hypothesis is mu is less than 13. My critical value is approximately negative 2.896. Here on this diagram, we have this all the way out here in the left tail, negative 2.896. The critical value actually represents a boundary that separates the tail from the rest of the graph, and depending upon all the information that we're given, that boundary moves a little bit. The next thing that we basically have to do is figure out what our test statistic is. We have to calculate that. For this problem, given all the information, and we're going to use this formula because this is when we have S or an approximation for S. So in this case, we have S, our sample standard deviation, and when we plug the numbers in, we get 12.62 minus 13 over 0.49 over the square root of 9, which gives me a value of negative 2.3265, and so on. So if I analyze this, let's take a look at the spreadsheet. If I analyze this, I have a critical value of negative 2.896, and I have a test statistic of negative 2.326 or 327, whatever it is. And now if I take a look at this image of the t-distribution curve, here is my critical value. My rejection region is just this little bit out here in the tail. And my test statistic falls over here, which is way outside of the rejection region. What we conclude is, since the test statistic does not fall within the rejection region, we must fail to reject the null hypothesis. And since this is a one-tailed test, and because we failed to reject the null hypothesis, in layperson's terminology we don't have enough evidence to suggest that the new species of garden snail is slower than the more well-known garden snail. And that's the end of this problem, and let's go on to the next problem.